Our first speaker is Gabriel Elvin from UC Riverside. He's going to be talking about avoiding monochromatic solutions to three-term equations.
All right, thank you so much. Yeah, so again, this is avoiding monochromatic solutions to three-term equations, and this is joint work that I did with my advisor, Dr. Costello, also at UC Riverside. So thanks, everyone. Let's get started. So we'll start with a fundamental question in graph theory, particularly with graph edge colorings. So if you have a large Kn and you want to color each edge blue or red, what's the best way to do so in order to avoid as many monochromatic triangles as possible? So monochromatic triangle here, I just mean a triangle where all three edges are all red or all blue. And I promise this will become additive combinatorics, don't worry. And so the question is, would coloring this complete graph completely randomly, give you the fewest monochromatic triangles asymptotically? Or is there a better way to color it which avoids more, some sort of like fine-tuned sequence of colorings in N where you can like get fewer triangles, fewer monochromatic triangles? And so, right, if you colored Kn randomly, you would expect 1/4 of all triangles to be monochromatic, just simply because 3 edges, 1/2 times 1/2 times 1/2, so 1 in 8 chance of being blue, 1 in 8 chance of being red, so 1 in 4 chance of being monochromatic. And so the question is, would this give the minimum? Would a random coloring, would 1/4 of all triangles being monochromatic be the minimum? Or could you somehow do better than that? And of course, we don't just have to talk about triangles. That was just some example to hold on to in your mind. But we could replace triangle with any graph small relative to Kn. So, right, 4 cycle, K4, some sort of tree, whatever graph you want. So given any graph H and a complete graph Kn, would random colorings yield the asymptotic minimum number of monochromatic copies of H? Or could you do better? So this turns into a big classification problem. For which graphs is coloring random essentially optimal, gives you the fewest monochromatic copies, and which graphs can you do better? And so we'll have terminology for that. If random is optimal, we'll call the graph common, H, and if random can be beaten, we'll call the graph uncommon. Okay. And so just a quick history of some of the graph theory results. So first in 1959, Goodman actually proved that K3 is common. So random is optimal for triangles. So that answers that first question. And then 3 years later, Erdős conjectured that Ks was common for all S. So random would be optimal for any small complete graph inside of the big Kn. And then a couple decades later, Burr and Rasta went even bolder with the prediction and said, you know what, probably all graphs are common. Random is optimal no matter what. In that case, that would be a pretty incredible definition for a classification, but maybe not as interesting if every graph is in the same class. And then in 1989, nearly a decade after that, Thomason actually proved that K4 was uncommon. So random can be beaten, and they found a sequence of colorings that beat random. And so that, of course, disproves those two conjectures and makes this question pretty interesting. So some other examples of common graphs, trees, cycles, certain bipartite graphs, and also uncommon, this graph. And this is not an exhaustive list. This is not a survey, but it gives you a sense of like, indeed, the terminology seems to fit pretty well. The more graphs seem to be common than uncommon. And so this work, I mean, there's still lots of work being done in this area, but this work led to a arithmetic analog. And so I'll just quick analogy with the triangles inside of the Kn question, right? So now we'll consider the equation x plus y equals z, that's taking place of the triangle, and the set of integers 1 up to n, that's taking place of the Kn. And so would coloring these integers randomly give you the fewest monochromatic solutions asymptotically? Or is there a better way to color those integers to avoid more monochromatic solutions? And here by monochromatic solutions, again, I just mean every integer that's in the input of the triple of the solution is the same color. So like for example, a solution to the x plus y equals z is 1 plus 2 equals 3. And so if 1, 2, and 3 are all red, that would be monochromatic, or all blue, that would be monochromatic. So that's the analogous question. And in 1998, Robertson and Zeilberger proved that the minimum proportion of monochromatic solutions to this was 2/11. And so this, and so this was done, you can tell from the timeline, it's done a little bit later. And we'll stick with the same terminology. That's what's done in the literature, right? If random is optimal, we'll call the equation common. And if random is unoptimal, or is random can be beaten, we'll call it uncommon. And so a corollary to this theorem, right? They found the actual asymptotic minimum. And the immediate corollary of that is that this equation is uncommon, right? Because from a random coloring, you would expect 1/4 of the solutions to be monochromatic for very similar reasoning as with the triangles, right? 3 inputs, as long as no 2 inputs are the same, each one has a 1/2 chance. So 1 in 8 chance of being red, 1 in 8 chance of being blue. And so you get 1/4. So this is uncommon. And this was a surprising result. I believe it was initially conjectured to be common because of the analogy and because you think, well, triangle, 3 edges, this equation, 3 terms, probably similar, but it actually turned out, so this was uncommon. So an immediate difference there. And so with this corollary, right, I'll just give you an idea, right? They found the minimum, and that's like the bulk of the paper is actually showing that that's the minimum, but a really quick way to show that it's uncommon is to use the coloring that they exhibited. So the proof sketch would just be here, look at this number line. And with this coloring, it's right, it's in terms of n, so it can be thought of as a sequence in n. If you count it, you actually would have to count the number of solutions here, but it is fewer than 1/4 of all solutions. It's 2/11 of all solutions. So that's a very rough proof sketch of showing it's uncommon. And so our result was really to generalize this corollary. And so what we did was we showed that every 3-term equation, so instead of x plus y equals z, we can now say ax plus by equals cz, where those coefficients are all positive integers. Every single equation of that form is uncommon. So random can always be beaten, no matter what the coefficients are. And here's just a quick example with one equation, and it gives you sort of some insight into how we found these colorings, right? Because all we had to do was for each equation, come up with a coloring that beat random, a coloring that can be a sequence in n. And so here's just an example of kind of our strategy for most of them. So we take a coloring so this equation x plus y equals 3z, right? Let's color everything remainder 1 mod 3 blue, everything 2 mod 3 red, and every multiple of 3 will color uniformly, randomly, and independently. That's just for easier counting purposes, right? If I say multiples of 3 are random, it's not technically a coloring per se, but we'll see how that goes. So this is what the coloring would look like. Black being random 50-50. And if you use this coloring, you can show that the proportion of monochromatic solutions to total solutions is 1/12. And remember, we're just trying to beat 1/4. That would be what you would get from completely random. And so, of course, if there's a random coloring, like with the multiples of 3 being random, if that beats it, well, then there must exist an actual coloring that beats it, just pigeonhole principle. And so this equation x plus y equals 3z is uncommon. And so to very, very roughly generalize this strategy, what you have to do in each case is find the appropriate modulus. Right here we did mod 3, and you have to find the appropriate pair to define the coloring. So you define the coloring, you pick one set of remainders and you pick another set of remainders, you color them opposite colors, and you color everything else randomly. Oops. And so that's kind of how we went about it for most of these equations. Of course, that strategy didn't work for every single equation. There were some that were left out. And so the ones that are left out, you can see are of any of these forms. The first 3 you'll see are like actual whole sets of equations, right? That we couldn't capture. And then the last 2 are actually individual equations. And so there are these 5 sets. But fortunately, there are some previous results that really help us out here. And these are actually really the only results done on this question. So I thought that was pretty interesting, and it ended up helping us out a lot. So in 2010, Butler, Costello, and Graham showed that equations of this form, ax plus by equals a plus b times z, are uncommon. So that takes care of that first set of equations. And then Robertson and Zeilberger in 1998, and Thanati, Pananda, and Wang in 2017 gave us this result. I combined their two results. Equations of the form x plus by equals z are uncommon. And so I'm combining them just by saying, when b equals 1, that was Robertson and Zeilberger. And when b is greater than 1, that was Thanati, Pananda, and Wang. And for this last result here, I should say that both groups of people, Robertson, Zeilberger, and Thanati, Pananda, Wang, showed they actually found the asymptotic minimum. And then an immediate corollary was that they're uncommon. So they proved stronger results for this. And these are the only equations where the minimum is actually known. And then Butler, Costello,
quick question by Galen is whether this Butler is plenary speaker Steve Butler or a different.
It is,
Butler.
yes. Same Butler. Yeah. And so that takes care of the top two sets that I have up there. And so we're still left with these three. And so how we did these last stragglers were we just found explicit colorings and use various counting techniques to show they're uncommon, that they'd be random colorings. So not really an example or a proof or anything, but just as a quick example of what this coloring might look like, for this equation, x plus 2y equals 6z, we used this coloring, counted it with some indirect counting techniques, and we were able to show that it was uncommon. And so that gives us our theorem. I'll just repeat it here, right? Every three-term equation is uncommon. So no matter what the coefficients are, you can always color the integers 1 up to n so that there are fewer monochromatic solutions than what you would expect from a random coloring. And of course, why not conjecture about any equation in any form? So here's a general equation. We have r terms on the left, s terms on the right, coefficients in n. And so we believe that any equation will be common if and only if there's the same number of terms on both sides, and you can partition them so that they sort of pair off into equal sets. So if there's a 2 on the left, there better be a 2 on the right, and et cetera. And that's the only equations that would be common. And so if, for example, this first equation we think common, second equation we would think probably uncommon, and this last equation probably uncommon, just because there are an odd number of terms. And so again, this terminology sounds backwards if you look at our conjecture, and you would think, oh, well, why are most equations uncommon? But again, that terminology comes from the graph theory. So, and of course, if you're studying linear equations with integer coefficients, you can replace this set of integers with any finite abelian group. And so, for example, this equation, x plus y equals z, is uncommon over n, as we saw, but common over the cyclic group of order n. So maybe that was the better analogy for triangles in a graph. And in fact, it was. And there is actually a theorem, not for any group, but as for a specific group, Fpn, still asymptotic in n. For that group, an equation it's been fully classified by Fox, Pham, and Zhao. And they showed that an equation is common if and only if there's an odd number of terms, or if there's an even number of terms and you can pair them off, similar to how we said before. So if you compare the conjecture that we had on the previous slide to the theorem, this theorem over Fpn, when there's an even number of terms, we expect the same behavior. They're only common when you can pair off the coefficients to either sum to 0 if you're over Fpn or to be the same. But then with an odd number of terms, it's completely opposite behavior, right? Over a group, common, and over 1 to n, uncommon. And so there's still more open questions, plenty of. Right, all we did was like find upper bounds on the minima, right? We didn't work on lower bounds at all, just that's the nature of showing something is uncommon. And so, for example, if we go back to our original coloring of x plus y equals 3z, but instead of coloring the multiples of 3 randomly, if we color the multiples of 3 like this, it seems to work really well, but I'm very perplexed as to why. It's a highly regular, it's 6 blocks, nice on the multiples of 3. Don't know why, but it works well, and I'd like to figure that out. Again, partially or fully classify equations as common or uncommon over the integers 1 up to n or arbitrary Abelian group. Study systems of equations, right? There is work on this already, but not much is known about systems of equations, right? You could ask the same about systems, right? Solutions to a system instead of solutions to an equation. And the most work that's been done on this that I've seen is on 4-term arithmetic progressions, which is a system of 2 equations. You can work with more than 2 colors. Why not? 2 colors is hard enough, but if you want an extra challenge, work with 3 colors or more. And then while you're working with more colors, you could also ask the opposite question. How could you maximize the number of rainbow solutions? Instead of minimizing monochromatic solutions, how would you maximize rainbow solutions, solutions where every input would be a different color? And then of course there's more, they just don't fit on this slide. So thanks so much for your attention. Really appreciate it. Special thanks to the GSCC organizers and to my advisor for working with me on this project. So I'll take any questions now happily.
All right, let's thank Gabriel first of all. And I know that Galen snuck in with a question a little before the end of
sorry, I couldn't see the chat.
Back to the definite. Oh no, I'm gonna watch it. Don't worry. Can you flip back to the definition of uncommon?
Yes. Where is it? I mean,
well, Galen, you can say more. I know you had some thoughts.
It's not a very official definition here, but
yeah, I like sort of don't fully understand. So like I somehow missed the intuitive understanding of common and uncommon, but it almost seems like when you're looking at sort of solutions to Diophantine equations, like this is very like classical number theory, and my algebraic brain almost says like, oh, why aren't we studying varieties? Like, what is the statement here that says, what is the variety statement? And I don't see it immediately, and I was wondering if maybe if I like looked back at some definition of common or uncommon, if I could like phrase this question in some kind of legitimate or official way.
Yeah, so I mean, I could give you maybe a more precise definition. I just kind of wanted to avoid that for this talk, but really like for 3-term equations, 1/4 is random, no matter what the coefficients are. So if you can find a sequence of colorings for, such that for a sufficiently large n, the proportion of monochromatic solutions to total solutions always stays asymptotically below 1/4. Stays away from 1/4. And I don't know if that helps or not, but yeah, I'm not sure. But I mean, it's interesting to think about, definitely. Yeah, thank you.
Well, thanks. It was a really fun talk.
No, appreciate it. Thanks.
Yeah.
Are there any other questions?
All right. If not, let's thank Gabriel again and